Welcome everybody to our first seminar of the season. Bhishan Jacelon will talk about genericity in the classifiable category. Go ahead, Bhishan.
Thank you, Anne. It's nice to be back in Prague. I feel like I can say this even being a local, given the variety of latitudes and longitudes I've lately found myself in. I will explain the title as I go along. And I really intend for this talk to be accessible. I don't want it to be too technical. So if you have any questions at any point, please do jump in. Okay, first of all, what do I mean by the classifiable category? I mean, the objects are going to be C-star algebras, nice C-star algebras. So unital, simple, separable, nuclear, Z-stable, satisfying UCT. Not important for us to understand what all of that means. I'll say a little bit about what Z-stable means. And the morphisms are just the usual ones, star morphisms. Most of the time, I will just focus on unital objects and unital star homomorphisms. But towards the end, I want to say a little bit about very non-unital algebras, so stably projectionless algebras. And in this case, I want to assume that the algebra is not just simple in the C-star sense, meaning no non-trivial closed two-sided ideals, but I mean algebraically simple, no ideals, algebraically. And I'll make some assumptions about the trace space, it being compact and some kind of non-degeneracy things. Okay, whatever nice things I need to assume in the non-neutral case, I will assume. Okay, so the basic question is, what do generic, whatever that means, objects morphisms in this category look like? So I will explain what I mean by generic. But first, let me just say a little bit more about this classifiable category. So I'm calling it the classifiable category because it's classified by the Elliott invariant. It's this thing I have here. So, okay, just very briefly, K0, K0 plus and it's 1A. This is the ordered K0 group. This is containing information about projections. K1, it has information about unitaries. T of A is the set of traces on the algebra, and I'll explain in a little bit more detail about traces. And R of A is just a pairing between traces and K-theory. Okay, so with this gadget, this functor, objects in this category E are classified. So you can detect isomorphism just by detecting isomorphism of this Elliott invariant. And it's functorial. So any isomorphism at the level of the Elliott invariant lifts an isomorphism of the algebra. As for what does Z-stable mean, so this Z, the Jiangsu algebra, is the unique object in this class. So its objects are classified by this invariant. So it's the unique object that has this exact same Elliott invariant as the complex number. It's infinite dimensional. And what does Z-stability mean? Z-stability means that A is Z-stable if A is isomorphic to A tends to Z. And there are some examples of Andrew Thomas from 15 years ago, whatever, that if you want to move outside of this category of Z-stable C-star algebras, the Elliott invariant doesn't work so well. So he constructs examples of one algebra that's Z-stable, the other is not, but they have the exact same Elliott invariant, so they can't be isomorphic. But you can't detect that in the Elliott invariant. Okay, so now let me say a little bit about what I mean by generic, as far as generic objects and morphisms go. So the first sense is what is known as a Pressé limit. And maybe you've heard various people talk about these things if you're here in Prague. I will say I'm not going to give the precise definition of what I mean by this. I'll just explain by an example. So if you take the category whose objects are just matrix algebras, so it's not finite dimensional algebras, just matrix algebras, and the morphisms are unital star homomorphisms, then this forms what's called a Pressé class. So that means the following. First of all, you have this joint embedding property. If you give me two objects in the class, I can embed them jointly into a third. For matrices, just take tensor product. That way. Second, you have what's called an amalgamation property. So if you give me an object, and you give me two embeddings, then I can complete the diagram. I can find the fourth object and morphism such that this commutes. So in the case of matrices, things are finite dimensional, so you can expect commutativity actually on the nodes. But more generally, you would give a finite set F and a tolerance epsilon, and you want the diagram to commute up to epsilon on this finite set F. All right, and then these are sort of the kind of crucial properties, but there's some things happening in the background. There's the Cauchy continuity property, which is some kind of completeness axiom, automatic sister algebras, and you have the weak Polish properties, some kind of separability axiom, which will hold in all the examples I'll talk about. And I'm actually not going to spend a whole bunch of time talking about Cressy here. But anyway, once you have a class of objects and morphisms that have these properties, then there's a generic object that can be built out of objects in the class as an inductive limit, and that's called the Cressy limit of the class. In what sense is it generic? Very roughly, first of all, it's universal. So every object in the class can embed into the Cressy limit, and it embeds it in essentially unique ways. If you give me two embeddings, and again, you give me a finite set and epsilon, then I can find an automorphism of the algebra that pushes one embedding onto the other, up to epsilon on the finite set F. That's what I mean by approximately uniquely. Okay, so as far as this toy example of matrix algebras is concerned, this Cressy limit is the universal UHF algebra. So a UHF algebra, let me just remind you, it's an infinite tensor product matrix algebra. So the universal one is the one that has all possible sizes of matrix algebra appearing in that tensor product description, appearing as large as possible. So it's like M2 infinity tensor M3 infinity tensor M5 infinity tensor M7 infinity, etc. Okay, so it's quite straightforward to see this is the Cressy limit in this case. And a corollary of this is that Q is self-absorbing. Okay, so this class of matrices, it's closed under tensor products. The tensor product of two matrix algebras is still a matrix algebra. The class is closed under tensor products. So therefore, Q tensor Q is also a Cressy element. So therefore, by uniqueness, the Cressy element is unique, they have to be identical. All right, okay. This is a bit of a ridiculous proof that Q tensor Q is isomorphic to Q. I mean, this is really just some linear algebra to prove this. It's ridiculous to go through the whole machinery of Cressy to do this. But the point is that you would hope for something similar for more complicated Cressy limits, like the Jiangsu algebra here. So this Z, which I told you, this important object in the classifiable category, it's known to be a Cressy limit where the object, I'll just so you have an idea, I said prime dimension drop algebras, just to say what a prime dimension drop algebra is, looks like this. So it's functions from the interval into matrices with some boundary conditions. Functions. Okay, so at 0, I want it to be in here. 1, I want it to be in here. And okay, so this is what a dimension drop algebra is, and prime means I want the natural numbers P and Q to be co-prime. Okay, right. You can immediately forget that if you don't care, just letting you know what it is. Okay, so the objects in the Cressy class that gives you the Jiangsu algebra are these, together with a distinguished faithful trace on this guy. So objects are pairs, prime dimension drop algebra and faithful trace. And the morphisms are star homomorphisms that preserve traces, that send one distinguished trace on to the other. Okay, anyway, whatever. So Jiangsu algebra is a Cressy limit, and you hope to use this uniqueness of Cressy limits, this framework, to prove that Z tensor Z is Z. By the way, so Ale, the other Ale Vinyati and I, gave a similar description for the scalar projectionist algebras W and Z0. I kind of talked about this last year. If this means nothing to you, don't worry about it. But okay, so as I said, so the reason for doing this sort of thing is to give a Cressy theoretic proof of a sort of self-contained proof that Z tensor Z is Z. And Said Ghassemi did manage to do this. But in the other cases, the W, the Z0 that I mentioned above, it's not so clear that it can be done. We tried very hard. But to me, a more interesting potential application is to investigate what's called extreme amenability of the automorphism groups of these various Caesar algebras. Okay, a group is said to be amenable if whenever the group acts on a compact convex set, there's a fixed point. That's one way of characterizing amenability. Extreme amenability is just remove convex from that description. So it's any action of the group on a compact space should have a fixed point. That's what extreme amenability is. Extremely amenable groups have to be very, very large. They can't be locally compact, for example. But anyway, so it's an open question to decide whether the automorphic groups of Z or W, they have this extreme amenability property. It's known for UHF algebras using what's called concentration of measure techniques. Ooh, I'm going to say yes. I'm going to say probably. But I'm not.
What is the topology on A?
It's a weak topology, not the normal topology. Okay, so if you want to do this using Decay Theory, you have to kind of verify this combinatorial Ramsey property thing. It's easier said than done. Nobody wanted to do it yet. All right. Anyway, this is all I want to say about this Decay Theory business. I just wanted to use this as a jumping off point. And here's where I want to jump to. All right. So I need to thank Tristan for pointing out this reference to me. So in the classical, what I'm calling the discrete relational hereditary Decay framework. So we don't worry about F's and epsilon. And we were talking about relational structures, whatever. There is a way of probabilistically constructing these Decay limits. So maybe some of you will be familiar with this Erdős-Renyi construction of the random graph. How does this look? You have countably many vertices, and for each pair of them, you toss a coin to decide whether to join them by an edge or not. Right? And the graph that you build in this way is itself a Decay limit. So, and they do a similar thing here in this theorem that I'm mentioning here. So they have these relational structures. So for each n tuple of generators, they toss a coin to decide whether they are related or not, essentially. And then they show that with probability 1, you get, that's what I mean by almost surely. You're not too familiar with this probabilistic language. So with probability 1, the structure that they build in this way is the Decay limit of their class. The question is, can we do this something similar for C-star algebra? This is quite sort of tantalizing in a way at first, because a lot of the important C-star algebras that we care about are given by generators and relations, including this Jiangsu algebra. But then you remember that this is what the presentation of the Jiangsu algebra looks like. So you think, okay, let's not do this. Let's take another approach. So that's what we'll do. Instead, what we're going to do is we're going to, our goal here is we're going to try to probabilistically construct these algebras, the universal UHF algebra, the Z, the W, whatever, in such a way that with probability 1, we're going to get these structures. And we're going to do that using the fact that they are inherently inductive limits. The way these inductive limit constructions work is that you have in mind an invariant that you would like your limit to have at the end of the day. So Q, UHF algebras are described by these supernatural numbers, just telling you the prime factors that appear in the tensor product description. So for Q, you know that you want to get all of the matrix algebras happening infinitely often. So step by step, you just put in more and more matrix factors. Z, you know, at the end of the day, you want your inductive limit of these guys to have a unique trace. That's what characterizes the Jiangsu algebra limits of these things. So you step by step try to get your trace kind of converging down to one point. So essentially what we're going to do is, instead of doing this deterministic procedure of getting closer and closer to a goal, let's at each stage make a random choice. And then at the end of the day, the invariants that we're interested in become random variables. And then we're going to ask, okay, what is the distribution of these various random variables? What can we say about them? So broad goal is to provide these probabilistic constructions. But then when we have this framework, this probabilistic framework, we can ask more broadly, you know, how likely are we to get at most K traces? How likely are we to get a purely infinite C-star algebra, whatever that means? All right, and the idea how we're going to do this is we're going to use random walk on graph. Take a graph, we're going to take a random walk, and then our position along the walk will determine the choices that we make at each stage. So let's do that. So to start with, let's take a simple random walk on the natural numbers with initial distribution little pi and transition matrix big pi. All right, what does that mean? So the natural numbers are here. I'm starting, little pi tells me that I start at a given position I with probability pi I. So I need to start somewhere. And then once I'm at a given position, this transition matrix pi tells me that with probability p, I jump up 1 to the next natural number, or with probability q, 1 minus p, I jump down to the natural number below. So I wanted to make a joke here. Well, I'll make a joke anyway. I was going to say, what we're going to do is we're going to construct a Q-deformed uniformly hyperfinite C-star algebra. Okay, anyway, the Q is just a probability. It's a joke. Okay, just wanted to get Ray's attention. Really. So here's a picture, which, by the way, okay, this actually does remind me of like maybe this approach of generators and relations, maybe it would be more amenable to something like a quantum group, and you have sort of more sort of friendlier presentations constructing a random quantum group. Okay, I don't know, we can talk about this later. Okay, so here's just a picture to describe what I was just saying. You jump up with probability P or you jump down with probability Q. And we're going to use this to construct a UHF algebra just by, okay, so what we're going to do, we're going to list all the primes, and we're going to tack on a matrix factor just depending upon where we are on the walk. Okay, so if y0, let's say we happen to start at 3, so we take n3, we take the third prime, and that's going to be our first matrix factor, right? And we just keep going like this. Okay, so this random walk is what's called an irreducible Markov chain. Markov chain basically just means that your movements are only determined by your current position and not where you've been in the past. Okay, so wherever you are, it doesn't matter what's happened in the past. Either you jump up with probability P, you jump down with probability Q. Irreducible means that if you start at any state I, then there is some non-zero probability of getting to any other state J. So the way this chain is constructed is it's irreducible. And I'm telling you this because the theory of irreducible Markov chain is very well understood. In particular, either every state is recurrent, so 0, 1, 2, 3, we call these states. So either they're all recurrent, which means that with probability 1, you return to them infinitely often. Okay, so either they're all like that, or they're all transient. Transient means with probability 1, you visit them only finitely many times. The transient means you're marching off to infinity eventually. So that means, and by the way, the first case, recurrence happens when Q is bigger than P. Q is bigger than or equal to P. That means we're more likely to march towards the origin, kind of keep going back like this. On the other hand, if P is bigger than Q, that means we're more likely to march off to infinity. So you get recurrence in the first case and transience in the first case. Okay, so what does that mean in terms of our UHF construction? If we're recurrent, that means we're hitting every prime factor infinitely often. So we get the UHF, the universal UHF algebra with probability 1 in this first case. On the other hand, in the second case, we get with probability 1 a UHF algebra of what I'm calling finite type. So each of the prime factors just appears finitely many times. Okay, so this is our kind of toy example for a random construction of a C-star algebra, and we indeed do get this Q with probability 1. Okay, so just a couple of remarks before I move on to some other constructions. There are lots of variations you can do, of course. So first of all, if we do this construction as I just described, we're going to get an infinite dimensional C-star algebra. We have infinitely many matrix factors. If we wanted to allow for finite matrix factors, we can limit. We can make 0 what's called an absorbing state. So if you ever get 0, you just stay put. You get tack on no more factors to give you a finite matrix algebra, and then you can compute the probability of that happening, the probability of your matrix algebra being its size at most A, whatever. Secondly, of course, there are many different graphs we could choose. So just as a simple example, instead of lining the primes up in a line, we could think, let's arrange them in a grid, some higher dimensional grid Z to the D. And the point is that as long as whatever graph we construct is irreducible, we'll still have the same phenomenon happening. Either we get this recurrence or we get this transient. So it's well known, it's a result from Polya back in the, I don't know, 30s or something, that, well, I don't know when, I can't remember when Polly was taken about. Anyway, whatever. So if we do this grid business, it's known that the walk is still recurrent if these two. So if we're in a city plan, but if we are higher dimensions, 3 or higher, it becomes a transit walk. So Kakutani has there's a saying attributed to him to describe this situation. So he says that a drunk man will always find his way home, but a drunk bird may get lost forever. A drunk man is... So because of this, I like to think of Q as the drunkard's Uhf algebra. So this is what I mean by this. So it's the classical kind of drunkard's walk. So a drunk is stumbling around the city street. He moves from intersection to intersection. By the way, simple symmetric, the words I have there mean that at a given point, you can move to any one of your neighbors with equal probability. So if in the grid, I can, up, north, south, east, or west with equal probability. So the drunk is stumbling around. If he ever gets to the bar, he stays there. But but in this setting, someone's put the bar out in infinity. So our poor drunk is just doomed to wander around forever, construct the universal Uhf algebra. Okay, so let's move now from Q to Z. And to do that, now our invariant is not going to be a supernatural number, it's going to be traces. So let me just tell you a little bit more about traces. Divisible by trace, I mean a tracial state. So it's a linear functional on a C-star algebra that's positive. So it tends positive elements of the C-star algebra to positive numbers. And it's of norm 1. That's what a state is. And it's invariant on the unitary conjugation. So this last condition, this trace identity, you can trace it in various different ways. You can say that trace A star A is trace A star. It is equivalent, definitely in it is equivalent. For bounded traces, it's definitely okay. Whatever, yeah. I phrased it this way for a particular reason. We'll come to that later. Okay. I'm going to denote by T of A just the collections of all traces on the C-star algebra A. If A is unital, this is a compact convex set when you equip it with the weak star topology. Weak star topology, I mean, so all of the elements of the C-star algebra, they give these evaluation maps on the trace space. The weak star topology is just the weakest topology that makes all of these continuous. It's a natural topology to put on T of A that makes this a compact set. But it's not just any old compact convex set. It's what's called a Chauffet-Simon set, which means the following. How can I say this briefly? So maybe a picture is the best thing. So when you encounter this weird Chauffet simplex, just think simplex geometrically like you would normally imagine. So 0-dimensional simplex, 1-dimensional simplex, 2-dimensional simplex, and etc. Okay. So this business about every trace, it's a functional on the C-star algebra. Okay, every element of the C-star algebra, it gives you this evaluation map. And what's a theorem due to Chauffet is that the trace evaluated an element is given by integrating this evaluation map over the extreme boundary of the simplex. All right. What do I mean by the extreme boundary? I just mean the extreme points as you see in this picture here. So these points would be the extreme boundary of these simplices. Okay. And what this means in the context of in finite dimensions just means that you have some points that are affinely independent, and you're taking the convex hull. And the extreme points are the ones that you cannot write as convex combinations of two different points. So they are as I indicated there. Okay, so it's maybe a bit much to digest what exactly I'm saying here, but just keep that picture in mind. Okay, so some examples. If you take a commutative unital C-star algebra, so continuous functions on some compact Hausdorff space, then this collection of traces is in one-to-one correspondence with the Borel probability measures on the space X. This is the Brice representation theorem. And so this trace space is very special. It's what's called a Bauer simplex. So the extreme points in this example are exactly the points in the space X, just given by point evaluation. So every point in the space X gives you a trace just by sending an element F of the C-star algebra to F of X. So this evaluation map is a trace, and these are exactly the extreme points. And the X by assumption is compact, so the extreme boundary is compact. That's what a Bauer simplex is. And the second example is just the picture I've had here. The traces on a finite dimensional C-star algebra are exactly these finite dimensional simplices like so. And the general fact is that whatever showcase simplex you have in mind, you can realize as the trace space of a classifiable C-star algebra. Okay. All right. So this is just a very brief recap about what traces are. Don't dwell too much on the details if they are upsetting to you. Okay, so let's move now. So we constructed Q. Now let's try to construct this Jiangsu algebra Z. And as I said, the Jiangsu algebra is the unique simple object that can be built out of these things and that has a unique trace. So basically, what I'm going to do is I'm going to do some sort of random construction of limits of these guys by taking a random simplex, and I'm going to see, okay, what's the distribution of these simplices that I get? Just to provide some context for what I'm going to say, if this means anything to you. So Elias Farrar, Andrew Thompson, and Asger Turnquist, they gave what's called a Borel parameterization of the collection of metrizable showcase simplices. It's not at all important for us to understand what this means. It's just I'm going to do something very similar. I'm going to not give a Borel structure. I'm going to turn it into actual a probability space so we can compute the probability. Okay, so the way I'm going to do this, I'm going to use this theorem of Lazare and Strauss that every metrizable showcase simplex defined in this abstract way, it can be described actually quite simply. It's just an inductive projective limit, sorry, of these finite dimensional guys. So every simplex, whatever this abstract thing is, you can write as a limit of these things with some connection maps. But you can even say more what the connection maps actually are doing. So what it's doing, you can think of this simplex as living inside this simplex as the base. And this map, the map from here to here, is the map that just fixes the base. So everything in the base stays put. And this extra vertex gets collapsed somewhere inside. And it's enough to know what happens to the vertices, because then you just extend affinely. Okay, so we're just, these maps here are just fixing the base and collapsing some point down into the middle. And what I'm going to do to make this a random construction is I'm going to collapse the point to a random point inside the simplex. So I'm going to decide on some probability measure on each of these simplices. I'm going to use that to make a random choice for the collapsing map. But actually, I'm going to do another random process in addition to that. I'm going to use the same Markov chain Yn that we used earlier. To this time, it's not going to be telling us how big a matrix factor we want to tack on. It's going to tell us the dimension of the simplex that we want to have at our end stage. Okay, so remember, Yn, it's either jumping up a dimension. So if we are jumping up a dimension, let's just say we're doing this business of mapping the base, including it into the higher dimensional one, or it's going to be mapping down. And if we're mapping down a dimension, let's do this business of fixing the base and collapsing to a random point. Okay, so we have these two random processes going on. Okay, what I have on these slides, just exactly what I said in words. So let's skip through it. So we're going to construct a random simplex in this way. Again, I just said all of this in words. Okay. Let me give you an example of what kinds of simplices you can get if you do this random process. First of all, let us forget about the Markov chain part of the process. Let's just do this business of collapsing to a random point. So Q equals 0, so the Markov chain is just steadily marching one up to infinity. There's no random happening here. And the connecting maps are these random collapsing things. So the simplex you get at the end of the day, of course, will depend on how you make the random choice. So what probability measure you choose at each stage. So first of all, let's say that we have no randomness at all. Let's say we decide that we're going to collapse the extra vertex just to the center of mass of the base. That's what I'm saying here. So just collapse, do the obvious thing, collapse to the center of the base at each time. And then you can show that the simplex you get at the end of the day, it's the Bauer simplex. So that's one of these things with the extreme boundary compact. And this extreme boundary is sort of, it's the simplest possible Bauer simplex you can get. So the extreme boundary is just a conversion sequence with one limit. Next, something a little more complicated. Let's not just do the center of mass. Let's decide we're going to collapse to one of the vertices of the base. We pick one at random. and they collapse. Then you can show that with probability 1, the simplex you get at the end of the day is the Bauer simplex, where the extreme boundary this time is the counter set. And a little more complicated, let's not try to unpack exactly what I've written here, but if you do a suitable sampling of the base, you can get the Paulson simplex, probability 1 as your limit. The Paulson simplex is this, it is another example of a Fresnel limit. It's the Fresnel limit of all finite dimensional simplexes. And it's very complicated in the sense that the extreme points are actually dense in the whole simplex. It's not something you can easily picture. Okay, but whatever. So in fact, it's in general quite hard to see what simplex you're going to get at the end of the day, except in very special cases like this, which is why I've highlighted these special cases. Okay, all right. So that's what we're going to do. So we're going to build a random simplex, and then we're going to use what I've called here the Thompson-Jiangsu algorithm. This is just a way of, if you give me a random simplex, there's a standard way of building from that a limit of these guys, simple prime dimension drop algebras, such that the trace of the limit is exactly the simplex you started with. So that's just what I've written here. So it's a machine. Okay, so you input this simplex, the sequence of simplices, you crank the handle, and the output is you get a simple inductive limit with the right invariant. And I'm calling this an algorithm because there's no randomness to this part of the process. It's just a machine. So the randomness has already happened in the construction of the simple. Okay, so now finally we've built our random inductive limit, a random simple inductive limit of prime dimension drop algebra. And the question is, what can we say about which one we have exactly? So again, we have this dichotomy. If P is smaller than or equal to Q, that meant that we are in the recurrent case. So P, remember, means you're marching upwards. Q is you're marching downwards. If Q is bigger, you're more likely to be marching downwards and keep going back and back. So in particular, if we're recurrent, that means you visit the zero-dimensional simplex infinitely often. So that means you have a trace collapsing inductive limit. Okay, so infinitely often, we go just to something that collapses all traces just 1 point. But in this case, with probability 1, we get the Jiangsu algebra. In the other case, the transient case, that means with probability 1, we're marching off to infinity. So with probability 1, we get some potentially very complicated tracial simplex. It'll be infinite dimensional, and then just depending upon which measure you decided upon, you could get the Paulson simplex or this Cantor simplex or what have you. No, sorry, P and Q is probably a bad choice. Oh yes, indeed. No. P and Q are these probabilities that appeared in the yes. I do apologize for that. Yes. Yes. Sure. Yes, thank you, Andre. Okay, yes. Sorry, they're just the probabilities associated with the random walk. Right. Yes. That's unfortunate. Okay, and just a couple of remarks. We can variations you can do again. The way that this initial construction, the only way to get a finite dimensional simplex is you get in fact a unique trace, but you can allow for arbitrary finite dimensional ones just by again doing this procedure of making zero an absorbing state, and you can just take like the biggest simplex you ever reach as your trace case, whatever. And you can do a similar thing to get the W algebra. So that's not dwell on that. Okay. Right. So far, again, the general procedure I'm outlining is we're doing some random constructions and we're viewing the invariants as random variables, asking what the distributions are. So we talked about supernatural numbers. We talked about trace spaces. Now we're going to talk about what's called the radius of comparison. I'll just say this very briefly because this likely will not mean very much to many of you here. The radius of comparison is a measure of how far away you are. It's a numerical measure of how far away you are from having what's called strict comparisons. If you have R equals 0, this inequality I've written here, that's the definition of strict comparison. And just, I guess, know that if you are a Z-stable C-star algebra, then you have strict comparison. So this R, this infimum is 0 if you're in the Z-stable case. But if you're outside of this Z-stable case, you can get potentially anything as your radius of comparison. So the bigger the R is, you might think the further you are away from being a nice classifiable C-star algebra. And in fact, Andrew Thomas showed that you can indeed get arbitrary values for this measure, this radius comparison. The way he does this is, again, he builds a similar inductive limit where the building blocks are continuous functions on some big, huge product of spares. And the connecting maps are these diagonal morphisms, where these eigenvalue maps, these ones are just coordinate projections. So from one stage to the next, you're going from one big product of space to an even bigger product of space, and just taking some coordinate projections down from the big one to the small one. That's these things there. And to make the limits simple, you need to take some point evaluation. So that's what these things are here. And then this radius comparison thing is just given by these ratios, how many projection maps you have to how many point evaluations you have. If you have many more point evaluations, then that means that you're in the situation of what's called slow dimension growth, not guarantees that you are in this nice classifiable Z stable setting. But if you have many more coordinate projections, you have high dimension growth. That means that the dimensions of these products of space is getting very big, very far. And that means that in that case, you're very far from being Z stable. Okay, so again, we can just do the same procedure. At each stage, we don't make a definite choice of what we want this ratio to be. We make a random choice. And then there's a way of interpreting, this R is just a positive real number. There is a way of constructing random positive real numbers by taking, and again, a walk on a graph. So this time you can take a walk on a rooted binary tree. You think of the real number as essentially a number with a binary expansion, something 0.01011110, whatever. You can just construct these binary numbers digit by digit by taking a walk on a binary tree. You take the left branch, it's 0. Take the right branch, it's 1. You just take your walk, and every walk you can possibly take will construct a binary number. And you use that essentially as the way to construct this randomly. And what, I don't know, I find it very amusing. Maybe you don't, but if you do this walk suitably, you can actually get quite a reasonable distribution, reasonable probability distribution for this radius of comparison. You can even compute with it. You can compute the expected value and so on. Okay, let me not dwell too much on this. All right. So now we're going to do a bit of a leap. So okay, we started with pressure limits and sort of motivating the idea of these probabilistic constructions, which we wanted to do by random walk of the graph. But now instead, what we're going to do is take a random graph. So we're going to make the graph itself a random object. And then we're going to, I guess Karen will talk about this next week, graph itself a bit. So there is a way of constructing a graph, C-star algebra, which we're going to do to this random graph. And then we're going to ask, what does it look like? Okay, so first of all, what do I mean by a random graph? There are lots of different ways you can do this. Here's specifically what we're going to do. So we're going to fix an even number n, which is going to potentially grow to infinity. I'm going to fix some r that's between 3 and n. And we're going to form the random R regular multigraph by taking a union of perfect matching. What am I doing? Let's assume they're an even number. I pair you off at random. And then I do that again. And I do that R times. And I keep track of the pairings that I made by drawing a graph. For example, this one. In this case, n is 6, R is 3. So you can see each vertex has 3 edges coming off from it. And I make this a directed graph just by making arrows go both ways on each of the edges. Then when I have, I guess the way I've drawn it, it looks like I'm doing a bipartite construction. I'm not. This is just the picture. Okay, so once I have a graph like this, there's a standard way of constructing a graph C-star algebra, which Karen will maybe tell us about. And what you can say various things about this graph C-star algebra. First of all, it is what's called a Kunz-Krieger algebra. That's just because the graph that you get is a finite graph. It has no sinks or sources. So it's a Kunz-Krieger algebra. That means something to you. If not, don't worry about it. And asymptotically almost surely, which means that as n tends to infinity, the probability tends to 1. The graph C-star algebra is purely infinitely simple. And again, this is actually not so hard to show. It's basically because this random multigraph is asymptotically almost surely connected. And then you can verify that it has the right properties for being purely infinitely simple. But what's actually really interesting is that you can say something about decay theory. Okay, let me discuss this a little bit. So let's fix an odd prime P that's co-prime to this R minus 1, this regularity thing. And let's fix a Bayesian group K whose size is some power of P. Then the probability statement is this. All right, what is this saying here? So ZP here, I mean the p-adic integers. When you tensor this abelian group, this finally generated abelian group, with the p-adic integers, this is detecting the p-Silov subgroup of K0. Okay, that's what this is doing. This is the p-Silov subgroup. So we're asking for the probability that the p-Silov subgroup is isomorphic to K. You have to do something like this. You have to normalize at a certain Silov subgroup. Otherwise, if you just wanted the probability of being of any fixed group K, it will just be 0. So this is just something you have to do to get a meaningful K. Okay, so that's what's happening on the left-hand side. On the right-hand side, this infinite product is just some normalization factor associated to the prime P. Don't worry about it. This is where the interesting information lies. So this NK is some constant associated to the group K. And what's important for us here is that it is inversely proportional to the size of the automorphism group. Okay, that's the take-home message there. So the general principle at work here is that the more complicated the automorphism group, the larger it is, the less likely the group is to appear. That means NK becomes smaller, the probability becomes smaller. So in particular, what you can show is that the probability of this Silov subgroup being cyclic, if P is, imagine P is some very large prime, probability that it's cyclic, so Z P to the N, is much, much more likely than it being ZP to the N. That's something you will expect cyclic groups to appear much more often than higher, like more complicated groups of the same type. Okay, I should say, where is this coming from? I can't claim credit for this. And indeed, why did I choose this particular model of random graph for this construction? It is exactly so that I can appeal to the literature and extract a result like this. So this is really from work of Melanie Matchett-Wood, who's this Harvard mathematician who works in things like arithmetic statistics, fan-file groups, if you know what those are, and things like co-kernels of adjacency matrices of random regular graphs. And that is essentially how you compute the Decay Theory of these graph C-star algebras. You just have to kind of subtract the identity from this co-kernel. And then you have to check through Melanie's proof to see that it all works out and believe that it does. Wait, but I think it's really fascinating to me that we can actually say something about the Decay Theory of these random structures. Okay, but anyway, that's all that I wanted to say about probability. In the last the talk, let me move on to a different aspect of genericity, and that now is in the context of Polish spaces, so complete separable metric spaces, or separable metriable spaces. So in this, I think this notion of generic is a property that holds residually. So for at least a dense G delta set in your Polish space. What is the Polish space that I'm interested in? It is the automorphism group of one of these classifiable C-star algebras. I'm assuming that there are actually traces. I'm assuming, moreover, that the trace space is one of these nice Bauer simplices, the boundaries, this nice compact space X. And I'm equipping this automorphism group with the topology of pointwise convergence. This makes it into a Polish space, right? So we're asking for what are, here I'm addressing the question of what do generic morphisms in the classifiable category look like? Again, and generic in this setting means in this residual sense. Okay, so just a couple observations before we get to analyzing the genericity here. First of all, every automorphism of the C-star algebra at this level of C-star algebra, it descends to an affine homeomorphism of the trace space just by composition. Okay, so automorphism descends to automorphism at the level of the invariant. And because it is an automorphism, it has to fix this extreme boundary, which we're calling this compact space X. So it restricts from the other C-star algebra down to the trace spaces to some homeomorphism of the space X. And more than that, it has to, the map alpha has to fix some trace. That's not too hard to see, actually. I'm not saying it has to fix some trace on the boundary, but just some trace. And then just as I said kind of briefly, showcase simplex is one where there's a one-to-one correspondence by the traces and these measures that are living on the boundary. So in other words, the automorphism we start with, we're interpreting it as homeomorphism of a compact space that preserves some probability measure. It's what's called a probability measure preserving topological dynamics. And the point is, we know a lot about it. So I'm going to just appeal to the literature of such things, and I'm going to interpret genericity results in that context to the level of feature algebra. I'm going to do that via classification. So, but before I get to there, I'm going to specialize even more. So I said I want this trace space to be a Bauer simplex. I want this nice compact boundary, but I want it to be a very nice compact boundary. I want it to be a manifold, in fact. I want it to be a compact connected manifold. And remember, I said any showcase simplex does arise as the trace space of a classifiable feature algebra. So there are classifiable feature algebras to which this applies. Okay, anyway, so that's what I want X to be, compact connected manifold, and I want this mu, this measure that's being preserved, to be what's called an OU measure. OU means it's faithful. That means the measure of any non-empty open set is non-zero. Diffuse, meaning there are no atoms, there are no points with positive measure, and I want it to be zero on the boundary of this manifold, if there is a boundary. First of all, it's called OU after Oxtoby and Ulam, who showed that these assumptions are precisely what you need for the measure to be a homeomorphic image of Lebesgue measure in the case where X is the cube. Okay, so these conditions, faithful, diffuse, zero on the boundary, guarantee that there is a homeomorphism of the cube that pushes Lebesgue measure onto the measure in question. And if you're in a situation where this X has no boundary at all, then these OU measures are generic. They form a density delta function. So it's not outrageously ridiculous to focus attention on these special OU measures. Okay, so I'm going to outline for you a very general procedure of lifting generic properties at this level of topological dynamics up to the C-star algebra level, but I'm going to focus on two very specific properties. The first one is what's called weak mixing. Okay, this is a bit of a mouthful the way I've written it down. Okay, but let me explain how you should think about this. So this X, and here I know a couple have heard me say this before, so I'm going to paraphrase the words of with not Folio, not Erdos. Help me out, somebody. Anyway, okay. So the way to think about this is X is Martini that we're mixing. So X is we start with volume V of vermouth. I think in this book it suggested we start with 10% vermouth, although the other LA said it should be 20%. I don't know what your feelings on the matter are. So X is a Martini. H is a stirring map. So we're stirring a Martini, and we start with some volume V of vermouth. Stir, 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 stir many times, and becomes very, very large. And we're taking a sip from a region U. So this thing here is measuring the amount of vermouth, the proportion of vermouth that is in the region V that we're sipping from. Okay? And then this in here is sort of measuring the proportion of vermouth in the total. So what this is saying is that if we stir many, 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 many times, we start sipping, then most of the time we're going to have a perfectly mixed drink. But very occasionally, we're going to have a drink that's too strong with too sweet. This is how you should interpret weak mixing, okay? It's a strengthening of being ergodic. You know what that means. If I got rid of the absolute value sign, that would exactly be being ergodic. And if I got rid of the average that I'm taking, that would be strong mixing. Okay? So it's some kind of in between ergodicity and strong mixing. Okay, so that's one property that tends to be generic. Another one is what's called chaos, right? First of all, want this homeomorphism X, H of the space X to be transitive. Transitive means there is one orbit, there's at least one orbit that's dense. And secondly, I want the periodic points to be dense, so points with finite orbits. I want these to be dense in the space X. I guess what I didn't write here, but if X is an infinite compact space, these two properties imply what's called sensitive dependence on initial conditions. So that means that however close you want, there are points that are very, very close together, but if you apply them up enough times, they become far apart. So this is sort of why it's called chaotic. So the theorem from topological dynamics, or the combination of theorems that I'm applying to, is that in this setting where we have a compact connected manifold and we have this OU measure, then in this space hx mu of mu preserving homeomorphisms of x, these two properties are typical: weak mixing and this chaos. Chaos if the dimension is at least 2. Okay, so just some examples of systems that have these properties. Irrational rotation of the circle is neither. So it's not chaotic because it has no periodic point at all. It's irrational rotation. And it's not weakly mixing. That takes a little bit more time to show. But it is an example of a map that is weakly mixed, ergodic, but not weakly mixing. So it shows weakly mixing with a strictly stronger property. So an example of a map that does have both properties is this Arnold's cat map business, which is the prototypical example of a hyperbolic toral automorphism. So we have this matrix 2, 1, 1, 1, and the reason it's chosen is that it has these irrational eigenvalues. 1 is bigger than 1, and 1 is larger than 1. We're thinking about it as a sort of moving point around the torus. And the point is that in the direction where the eigenvalue is bigger than 1, it's going to be stretching things out. And in the direction where it's smaller than 1, it's going to be compressing things together. And it's also an example of what's called an Anosov diffeomorphism, and it is the measure that it preserves is just the volume measure on the torus. It is not just weakly mixing, but just strongly mixing. And in fact, it is transitive, in fact, even stronger, what's called topologically mixing. And as for the periodic points being dense, every point with rational coordinates is periodic. Here's a picture I just got from Wikipedia to illustrate why it's called Arnold cat map. So if you think this is cat pixelated, the pixels lie at point rational coordinates. That means that if you apply the map many times, sufficiently many times, in between, it's going to be distorted, stretched, and compressed in all sorts of ways, but eventually it gets back because the points are periodic if you have rational coordinates. Okay, so this is an example of something that is chaotic and weakly mixing. All right, so the theorem. Now, as I said, I'm just going to interpret these genericity results from topology up to C-star algebra. I'm going to do it using classification. So here's the setting. I have one of these nice classifiable C-star algebras. I want the extreme boundary to be this nice compact connected manifold. And then I also want some K-theory conditions, which I maybe explain a little bit later, but they are satisfied for large class of examples. For example, these AI algebras, whatever that is, inductive limit of interval algebras. And let's fix a trace that is an OU trace. Remember, I'm thinking traces are in one-to-one correspondence with measures on the boundary. So I want the measure corresponding to the trace to be this nice OU measure. Then the statement is that the typical, so for at least a dense G delta set of automorphisms, the behavior on the level of the trace space is weakly mixing and chaotic if the dimension is at least 2. Maybe let me just say a sentence about why I was interested in a result like this. If you are in the situation where the extreme boundary is just finite, you're in one of these finite symplectic conditions, what is the automorphism doing at the level of the trace space? It's just permuting. It's just permuting the extreme points around. There's nothing very complicated happening here. What this result is doing is that if we're in the non-finite dimensional setting, we have some manifold boundaries. Then the situation is very much more complicated. It's chaotic in a way. All right. Let me not go through the details of how it's proved, but it's just using classification. So what do I need to do? I need to start with a map, an automorphism alpha, and I need to find an automorphism beta that's close to it and that has the right properties on the boundary. And how do I do this? I just take my map alpha, I look at what it does at the level of the invariant. So the invariant has two kind of aspects to it. There's the K-theory part and the traces part. I keep the K-theory part the same, and I nudge the traces part to be either weakly mixing or chaotic. I know I can do this because of the resultant topology. And then I use classification to lift that to a morphism at the level of C-star algebra. And then I use classification again to say, well, if I have two morphisms and I know the invariants are close, then they have to be close. Up to conjugating by unitary, but who cares about that? Okay. In a nutshell, that's how this is proved. There's just a slight subtlety here. I mentioned that the LF invariant is this thing that classifies in classifiable category, but it only classifies objects. If you want to classify morphisms, which is what I'm doing here, you need to refine the Elliott invariant to include this thing that's called total K theory and how to twice out of the K1. Definitely don't want to get into. But just, I should say, these assumptions on K theory I have about K1 being torsion free and this RA map being constant, it's designed to sort of address the complicated nature of the refined invariant. Okay, whatever. So in a nutshell, that's what I did. You know what? I might just stop there actually, because I have some results about cross products, but I'll just very briefly say in which, let me just show you the corollary. You can do use very, very similar ideas. You can the idea meaning you can take whatever topological behavior you want happening at the level of the trace space, and you can lift it up to the level of the C-star algebra, and you can lift it in a way that has nice properties. You can use this to prove a range result for cross products. So you can show that any classifiable KK contractible C-star algebra, KK contractible means no K theory at all. So these things are very non-unital, they're stably projectionless. So every one of these stably projectionless, no K theory classifiable guys can be written as a sort of very nice cross product using the similar idea. But okay, let me stop there.
Any questions?
Okay. What do you mean by manifold here? Is mean that they have a sub-different? Ah, okay. Because not any differentiable structure. Okay. Thank you.
Yeah, sure.
Yeah, can you hear me?
Yeah, go for it.
Yeah, I already asked you this last week, but anyway, how likely it is to
some sort of a limit in the category?
It needn't be an object in the category. Yeah, so the category here, the category here you think about is the finite substructures. The first limit is you're trying to build the limits, build the structure you're interested in as out of its finite dimension or finite substructures. So the category only has these finite. Yeah. You need a metric enriched category. So talk to Jacelon. Yeah. Yeah, absolutely good point. So here, this F and this epsilon is something you need in outside of setting of finite dimensional C-star algebras. But yeah, as Tristan was saying, without this, yeah, you can phrase it totally category theoretically.
Hell is it?
Usually in two categories. So you have
Okay.
a smaller category where you take a process sequence.
Yeah.
And that exists, the sequence exists in the smaller category. And then the limiting object, that will be the limited
In the
larger
larger category. Okay. And so
That's just something very special about this example. Yeah. But it's a very relevant point, because I mean that's kind of what Sai did to he included these tensor products of the objects in the category, but he doesn't get this narrow amalgamation property. He gets the weak amalgamation property. Yes. But it's, could be. Yeah, I guess, yes. The NWAP. How likely is amalgamation properties functorial path to a given continuous function? Yes, very good question. Yeah, Laurent. I guess Laurent has the Kuhn semigroup in mind. Yeah, so Laurent, I don't know. Yeah, I think it's a good. I'm not entirely sure. Like if you. I feel like, yeah, if you're in a nice enough situation, like these Lionel classifiable situations, I feel like, yeah, you should be able to just hit it with the Kuhn functor and you should be able to get an amalgamation, I would think. But you know, we should talk about this one for sure.
Yeah. But you need a metric, like metric enriched category.
Oh. Ah, yes, go ahead, please.
Hi, can you go back to the last slide? Just to see the result. Hello,
I can't hear you if you're
can you hear me now? Hello? Hello?
doesn't make it one. Yeah.
Hello? Can you hear me now?
Yeah, maybe you can just type. But actually, maybe sort of relevant to go to the last slide, I think. So we can navigate this more effectively, probably. This slide, I guess. Yeah, I mean, if you, this is on the archive. This not the first part of the talk about the probability stuff, but the last part, like this slide would be. Do you assume something on alpha? Yes, basically, okay. So the theorem of which this is the corollary. This alpha is going to have finite Rockland dimensions. That's how you know, whatever that means. So you start with some action on the trace space and you lift it to no optomorphism, but in fact, you can use results of Szabo, Wu, and Zacharias to show that this alpha has this finite Rockland dimension. And this is a very, very strong property. It tells you a lot. It tells you the cross product is classifiable. It tells you that the trace space is exactly the space of invariant traces on the action without commuting towers. Yes, without commuting towers. That's right. Yeah. But that's enough to get to the nice property. Yeah, no problem. Yeah, maybe I just want to make this comment to what Muraz is saying about the manifold structure. Yes, topological, but I really also been trying to put a Lipschitz structure on it, because I guess maybe there is a notion of formulation of Lipschitz manifolds, but I've just, when you have Lipschitz maps, then you can really observe. So I gave you this example of this Arnold's cat map, which is this nice chaotic map. But you can use Lipschitz elements, Lipschitz continuous functions in a manifold to kind of detect various features of this chaotic system, like the central limit theorem and all these kinds of nice things. Then I've been trying to kind of develop a Lipschitz structure in the C-star algebra itself to have a suitable interpretation of these phenomena. Okay, anyway, I wanted to get that out there. My goal is to somehow marry this all together. I want to have like the marriage between compact quantum metric spaces and the classification program. This is my pipe dream somehow. Yeah. Yeah, I've really been trying to do this similar thing, but on the trace space, not the state space. I even like maybe prematurely wrote a paper called Metrics on Trace Spaces, like with me a nod to Riefeld's metrics on state spaces. But no, kind of long thing. What's the question, please? The question was just asking, what is the compact quantum metric space? I guess. And it is in the sense of refill. Okay.